Finding height and velocity. In the drop ball example, we calculated the gravitational potential energy at each height using this formula right here. Since the total energy remains constant, we could then calculate the kinetic energy at each height. That would equal the total energy minus the GPE. And as you go down, GPE decreases, which means what? It means kinetic energy should increase. So if we're given the GPE instead of the height, we can find what height the ball is by arranging the first equation right here. Right? We want to solve that for height, so we divide both sides by mg. Okay, the mg cancels out here. We're left with height is equal to GPE over mg. Once we know the total energy and the gravitational potential energy, we can now find kinetic energy from kinetic energy equals total energy minus GPE. We then substitute in for kinetic energy 1/2 mv squared. That will allow us to solve for v. So we start with our kinetic energy equation here, and we undo the multiplication of 1/2 on the right side of the equation to isolate v squared. And you know what? We're going to do 1/2 and m at the same time. So we divide ke, the left side of the equation, by 1/2 mv squared, and we divide the right side of the equation by 1/2 mv squared. So what do we get there? Well, let's see. Let's look at the right side. This 1/2 m will cross out this 1/2 m, leaving us with v squared times 1, which is v squared. On the right, we have kinetic energy divided by 1/2 m. So that means we keep m in the denominator and 2 pops up to the numerator. So we get 2ke over m. We then take left side, move it to the right. Oh, I'm sorry, that was right, move it to the left, move it to the right. And we have v squared is equal to 2 times the kinetic energy divided by m. But what do we do now? We need to undo v squared to get v. Undoing squaring a number is called taking the square root of the number. And whatever we do to the left-hand side of the equation, which is v squared, we have to do to the right. So here's our equation. We take the square root of both sides, right? This is the square root sign. And then the square root of v squared is just going to be v. So v will equal the square root of 2 times ke over m. So once we have the kinetic energy and m, we can solve for the velocity of the ball at every height. Let's do an example. We have an object with the kinetic energy of 1,000 joules and a mass of 10 kilograms. What is its velocity? We have our equation here. V is the square root of 2ke over m. Substitute in kinetic energy and the mass. Divide 1,000 by 10 and we get 100. And the units will be meters per second outside the square root sign. Taking the square root of 100 is you have to find what number times itself will equal 100. And that actually happens to be the number 10, because 10 squared, which is 10 times 10, is equal to 100. So the square root of 100 is 10. So our velocity is 10 meters per second. We can now predict how fast the 1 kilogram ball will be going if you know how far it has fallen. So we have different heights here. We start up here at 3 meters and use conservation of energy to determine the missing values. And these equations here. Total energy is GPE plus KE, which is a constant. GPE equals mgh. And again, we know that g is equal to 9.8 meters per second squared. That's the acceleration due to gravity. But we're going to set it equal to 10. We're allowed to do that for simple calculations like this. And then we can find kinetic energy by subtracting gravitational potential energy from energy. So give a shot here, and let's start with the top one. What's our velocity at the top? Well, it's at rest, so it's 0. So what's our kinetic energy? That also will be 0. So what is our gravitational potential energy? Well, it's mgh. So I'll just talk you through it. Mass is 1 kilogram times 10 meters per second squared. Well, that's number 10. Times the height 3, and we get 30 joules. So that's our GPE. And since there's no kinetic energy, that also is our total energy. You know what? I'm going to sneak down here. Put total energy is 30 joules at each point because of the conservation of energy. So please work on filling the rest of this out and go to the next slide to check your answer. Now you can predict how fast the 1 kilogram ball will be going if you know how far it has fallen. Well, hopefully you can. I hate to presume people can do anything, but let's see if we can work through this. Use the conservation of energy to determine the missing values. We have them all put out here so we can just talk through it. We have to start at this point here. That's where we know all the energy is GPE because the ball is at rest. So GPE is mgh, so we'll multiply the mass times g, which is 9.8 meters per second squared, times the height, which is 3 meters, and we get this answer here, 29.4 joules. You're at rest, so that means no kinetic energy and no velocity. Why? Kinetic energy is 1/2 mv squared. So our total energy is all locked up in GPE. That won't change because there are no outside forces, no external forces, so we can fill that column in. Now let's go back to GPE for 2 meters and 1 meter. Once again, we use mgh, and we come up with these numbers, and then it's 0 at the bottom. Our next step, like we did earlier, is to find kinetic energy. Well, kinetic energy will just be the total energy minus the gravitational potential energy. So we already have at the top it's 0, here it's 9.8, here it's 19.6, and here all of it is kinetic energy. Now we need to find velocity. So we look at this equation here, we isolate v, so multiply both sides by 2 over m. So we'll get 2 ke over m, and that's equal to v squared. So velocity, you have to take the square root of both sides, right? Because square root of v squared is v, and you get the square root of 2 ke over m. And what numbers do we plug in there? Well, here's our kinetic energy, and here's our mass, 1 kilogram. And at the top you have 0, which is what you expected, you were at rest, and then it increases. At each step it's going faster until at the very bottom it hits at 7.7 meters per second, which is about 15 miles an hour. That's pretty fast for dropping a ball from only 3 meters height. With roller coasters, and often with ski slopes, the motion is up and down. We'll use a ski slope as the problem solution is the same, and this time we get to look at some nice evergreens in the background. The total energy is the same at every point along the slope. Here's point A, point B, point C. E represents the total mechanical energy, and it shows that the total mechanical energy at point A, B, and C is the same. The total mechanical energy at every point can be represented as the sum of gravitational potential and kinetic energies. So here we go. Our total mechanical energy equals the GPE plus KE at point A, at point B, and at point C. We then substitute in our values for GPE, which is mgh, and then 1/2 mv squared for KE for each point. And the subscript here tells you where you are. Okay, so there's C, there's point B, and there is point A. We're going to start at point A. We have the skier over here, and we're going to assume that that skier only has gravitational potential energy and no kinetic energy. Why no kinetic energy? Skier's not moving. Skier's about to move, but not yet. We're going to set this level right here, where the skier at point B is. Of course, it's the same skier. I'm talking about the skier like it's different people. We're going to say that's the point where GPE is equal to 0. So at point B, that skier will have no gravitational potential energy, but will just have kinetic energy. And then the skier at point C, it's like time-lapse photography, will have both GPE, because that skier is above the 0 reference point for gravitational potential energy, and will also have kinetic energy because the skier is moving. We can now take this equation here and remove the quantities that are equal to 0. So at point A, we said there was no kinetic energy, and at point B, we said, what did we say about point B? There's no gravitational potential energy. And at point C, it has both of them. So point A is just mgh, point B is just 1/2 mv squared, and point C has both gravitational potential energy and kinetic energy. So let's see what happens as the skier moves from point A to point B. And that's point A to point B. We are only interested in the skier's energy at points A and B, so our conservation of energy formula reduces even further. What does that mean? We don't care about this C part, so we're just going to exit out, and our total energy will equal mgh at A and 1/2 mv squared at B. And we're going to write that down right here. Now, an interesting point. We didn't say if the skier slid right down here, or curved back and forth and came here, or maybe jumped up a little and came down. It doesn't matter. That's the beauty of using conservation of energy. We don't care how the skier got there, or the roller coaster. Again, with the caveat we're ignoring friction, that would change the game. We just care final position and initial position. So what if we're given the height of the hill, which we are, it's 20 meters, can we solve for the velocity of the skier at point B? Yes. Would not have asked the question if we couldn't do it. Here's our equation here. mgh at point A equals 1/2 mv squared at point B. So we have mgh at A equals 1/2 mvb squared. What do we do next? Well, we repeat the equation here, except what did we do? We switched the left and the right side because we're trying to solve for VB. Next, we multiply both sides by 2. We undo the operation of dividing this by 2 by multiplying both sides by 2. So 2 cancels here, and a 2 winds up on this side, 2 mgha. What's the same on both sides? The mass. We cancel out the mass. So we have VB squared equals 2gh sub A, and our velocity will be the square root of 2gh sub A. What's really cool there is the mass of the skier cancels out. The velocity of a less massive skier would be the same as a more massive skier. Use the conservation of energy in the formulas for GPE, KE, and V to complete the table for the ski slope. The skier's mass is 50 kilograms, so please work this exercise. And let's just go ahead and write them here. The equations GPE is mgh, KE is 1/2 mv squared, and the velocity is the square root of 2gh. All right, we got that from the previous slide. So I'll do one of these. At the top, you have 0 velocity, so all of your energy is in GPE. So let's put a 0 there for KE. At the bottom of the slope, there's 0 GPE. So let's go ahead and calculate the initial GPE. It's going to be the mass of the skier, which is 50 kilograms. I'll save the units for the end. 50 kilograms times g, we're using 10 meters per second squared to approximate the 9.8 meters per second squared, which is really what g is. And we times that by what? The height, which is 20 meters. Okay, I'll just leave that out. You multiply all three of them and you get joules. And we'll put a joules here so you don't have to repeat the unit in each one of the boxes. So what does that equal to? 500 times 20? 500 times 10 is what? 50 times 10 is 500. 1,000, 10,000. 10,000 joules. So that is also the total energy. So put that into the columns here. And please fill out the rest. And once you find kinetic energy, actually you'll be finding this first, and then going over and finding the velocity using this formula. Use the conservation of energy in the formulas for GPE, KE, and V to complete the table. The skier's mass, I'm going to need that, is 50 kilograms right over here. That's mass. Well, we've already got the table completed, but if you don't know how we did it, it's not terribly helpful, is it? So let's go through it. All we have in the beginning is the mass and the height where the skier is at rest. Okay, we're going to assume he's rest here. They didn't say it, but we have to assume he's at rest. So we can calculate his GPE by mgh, and we get the GPE is 9,800 joules. He's not moving, so both the kinetic energy and the velocity will be 0. So you add these two numbers together. Total energy is 9,800 joules, and that will stay the same. We're assuming no friction as the skier goes down the slope. At point B, that's at the bottom, no GPE, right? Height is 0. So all the energy is in kinetic energy, so we can fill that in. And then to find velocity, we have kinetic energy is 1/2 mv squared. We isolate v by multiplying both sides by 2 over m, and that will cancel out the 1/2 m in front of the v squared. So you get 2 over m ke is equal to v squared. And you know what? I'm going to skip a step and take the square root of both sides, so I get v on the right, and I have this term here. Probably should draw a square root sign. There we go. Square root of 2 over m ke. So here's our ke. Up here is our mass. Put the numbers in, and we can find at this point your velocity is 19.9 meters per second. Then at point C, okay, here we are at point C, kind of, you know what, let me erase some stuff there. Be careful. I want to keep that ke there. So we have, where are we? We're at point C. We're at 5 meters high. So we calculate the GPE as mgh, and we get 2450 by using a height of 5 meters. Subtract that from the total energy. Here's our kinetic energy. Now I use this formula here. The velocity is a square root of 2 over m ke, and I get 17.1 meters per second. So the further down you go, the faster your velocity is because you have no GPE. You have less GPE. When the skier came back up to the point over here, some of that kinetic energy went into GPE, so the skier slowed down.